see the effect of friction in our oscillations. For that purpose, I'm going to work with a model system here. So we are trying to calculate damped oscillations. So in my model system, I have a block with mass m that is attached to a spring. The spring is displaced from its equilibrium position by an amount x. When that's the case, you know, we're going to have the spring force minus kx trying to pull the spring back. So this spring has a spring constant k. The block is immersed into a viscous liquid. So I have a viscous liquid here. So I'm going to observe the effect of the viscous liquid as a retarding force, as a source of friction in the oscillations of the block with mass m. All right. So in the case where you have non-conservative forces such as friction, the effect of the friction is mechanical energy is converted into internal energy. So there will be energy loss, mechanical energy loss in the system because the mechanical energy is used to heat the system, basically turning into heat, and that's going to increase the internal energy of the system. Okay, so we would like to obtain the equation of motion and solve it in order to see the effect of damping due to the friction in this situation. So we can draw the free body diagram for M. So what I see here is I'm going to have the weight of the object, mg. There will be a restoring force, kx. There will be a retarding force, r. And there will be a buoyant force, B. So let's talk about these forces. The retarding force, that is basically accounting for the friction in my system, force R, is typically modeled as being proportional to the velocity of the object but opposite in direction. And here we have a coefficient that characterizes the strength of this friction. B is called the damping coefficient. And I also have this buoyant force. The buoyant force B for an object that has been fully immersed into a liquid is the density of the liquid, the volume of the object times the gravitational acceleration. Basically, it's the weight of the liquid displaced by the object. Okay, so that's the buoyant force. And I also have the weight of the object mg here, and I also note that m, the mass of the object m, is equal to density of the object times its volume of the object. So if I write the net force in X, I will have mg minus bv minus kx minus rho liquid v object times g is equal to mx double dot. So you see here I have defined x to be vertically down. So that's the acceleration on x component, means it's the downward acceleration I'm looking at. So it's x double dot. Okay, so I substitute this into my equation and I obtain in the parentheses g v object rho object, density of the object, minus the density of the liquid, minus bv minus kx is equal to mx double dot. That's the equation of motion. Now I want to look at the case if v object is negligibly small. It's a very small volume. Then I can basically neglect this part, negligible contribution to this equation, and that is because the volume of the object is very small. So in that case, I'm going to obtain the following equation of motion: mx double dot plus bx dot plus kx equals to 0, where x dot is the velocity v. So eventually I have obtained the equation of motion for the damped oscillator, which I would like to analyze. Okay, so let's take this equation of motion and mx double dot plus bx dot plus kx is equal to 0. So if you don't know how to solve differential equations, you can always start with an ansatz and check to see if it solves the differential equation, and then try to understand the behavior from this solution. This is what is done in the notes. So here I'm going to actually solve this differential equation, and maybe this is the first time you will see how to solve a second order differential equation like this, ordinary differential equation. I have a characteristic equation that I obtain from this differential equation. Characteristic equation for this differential equation is my square plus by plus k is equal to 0. Basically, I replace the second derivative d square dt square with y square and d dt with y, and since I have no derivative here, it's going to be just k. So the solution to the characteristic equation is y1 2 minus b over 2m plus or minus square root b square minus 4mk divided by 2m. And the solutions will be found from the solutions of the characteristic equation. So I will obtain a solution if b square is equal to 4mk, the solution I will obtain will be x of t is equal to a times e to the minus b over 2mt. If b square is greater than 4mk, that is, it's a real number, the square root gives me a real number, then I will have a solution, a general solution of the form a times, let me call this square root b square minus 4mk divided by 2m alpha, a times e to the minus b over 2m t e to the alpha t plus b times e to the minus b over 2mt e to the minus alpha t, where a and b are arbitrary constants that are to be determined by the initial conditions. And if b square is less than 4mk, then I will have x of t is equal to an arbitrary constant a e to the minus b over 2mt e to the I alpha t plus b times e to the minus b over 2m t e to the minus I alpha t. Okay? So this last solution, this is the condition I'm going to look at first, can be also written as using an initial phase in order to account for the initial conditions. Alternatively, let's say, I can introduce a phase constant phi here. This will be a e to the minus b over 2mt cosine of omega t plus phi in this form. Okay, which is my ansatz to solve this equation if you don't know how to solve differential equations. Okay, so basically that solution comes from this case, and you have you basically combine with the same constants. A and b are the same. E to the minus b over 2mt, you have e to the I alpha t plus e to the minus I alpha t. That gives you cosine alpha t. But I have introduced an initial phase here in order to account for the initial conditions as well. All right, so if I look at this solution and try to verify if it satisfies my differential equation, I have to take a first derivative. So x dot is equal to minus ab over 2m e to the minus b over 2m t cosine omega t plus phi. Then I take the derivative of the cosine, I get a minus sine minus a omega e to the minus b over 2m t sine omega t plus phi. And basically what I have here is x dot is equal to minus b over 2m times x, a e to the minus b over 2mt cosine omega t plus phi, minus a omega e to the minus b over 2mt sine omega t plus phi. If I take the second derivative, x double dot, I will obtain minus b over 2m x dot. Then I will have plus a b omega over 2m e to the minus b over 2m t sine omega t plus phi, and then I will have minus a omega squared e to the minus b over 2m t cosine omega t plus phi. Okay, so here I have also encountered x again. So let's continue here. X double dot is equal to minus b over 2m x dot. Then I have here, basically this is minus omega square times x. So I have minus omega square x plus a b omega divided by 2m e to the minus b over 2m t sine omega t plus phi. So that is this term here. Okay, so at this point we're going to multiply both sides with m. So I will obtain m x double dot is equal to minus b over 2 x dot minus omega square x plus omega square x times m plus ab omega divided by 2 e to the minus b over 2mt sine omega t plus phi. And remember, mx double dot is supposed to be equal to minus bx dot minus kx. So this should be equal to minus bx dot minus kx, so that this solution satisfies this differential equation. So if I take minus bx dot to the left hand side, I obtain plus b over 2 x dot, and then I have minus m omega square x, and then I have plus ab omega over 2 e to the minus b over 2m t sine of omega t plus phi equals to 0. Now I'm going to substitute for x dot this result. So I have b over 2. For x dot I'm substituting minus b over 2mx and minus a omega e to the minus b over 2mt sine minus a omega e to the minus b over 2mt sine omega t plus phi. Then I have minus m omega square x. Then I have plus ab omega over 2 sine omega t plus phi times exponential b minus 2mt. That's equal to 0. So I'm going to distribute this b over 2 into this parentheses and put it in x parentheses. So in x parentheses I have minus b square over 4m minus m omega square and I also had a kx here, so I have to take that into account. So um, there is a plus kx here because of this one. So I'm going to have also a k. And the next term is minus ab omega over 2 e to the minus b over 2m t sine omega t plus phi. And you can see this will be cancelled with the plus term, plus ab omega over 2 sine omega t plus phi e to the minus b over 2m t. So this term is disappearing, so that's equal to 0. So when is this a solution of this equation? If you have what in the parentheses 0. So you have m omega squared must be equal to k minus b squared over 4m, or omega must be equal to square root k over m minus b over 2m squared. So if the frequency, angular frequency of the oscillations is given by this expression, then my solution a e to the minus b over 2m t cosine omega t plus phi applies. And as you can see here, if b were 0, then omega would be equal to omega 0, which is square root k over m. That is the case where you have no damping, and this is called the natural frequency. So that's the case where you have no damping. So you can write your angular frequency omega as square root of omega 0 squared minus b over 2m squared. Now this is going to be the solution in only one case, where you have omega 0 squared is greater than b over 2m squared. So if b over 2m is less than omega 0, then you will have omega a real positive number. Then we say that the system is underdamped. So the damping coefficient is too low. The system is underdamped. If we have b over 2m is equal to omega 0, then the omega that you obtain here is 0. So if you go back to my solutions, that's this case, b squared is equal to 4mk, and your solution is just an exponential decay. It's called critically damped. The system is critically damped. If you have b over 2m greater than omega 0, omega becomes imaginary, and basically it's the cosine is not the solution here. You don't have an oscillatory solution. That is this second case here. You have a combination of exponential decays, and in this case you have the damping coefficient too big. The system is overdamped. All right, and the response that you obtain depends on the value of omega. So if it's real and positive, it's underdamped. If omega is 0, you have no oscillations. The system is critically damped. If b over 2m is greater than omega 0, omega is imaginary, no oscillations, the system is overdamped. Now we can see this behavior, underdamped, critically damped, and overdamped, by plotting x as a function of t, the solution. In the first case, when the system is underdamped, your solution is e to the minus b over 2mt cosine omega t plus phi. That means we have an exponential envelope, and the system keeps oscillating following a cosine function, but the oscillations are damped. So this exponential term, e to the minus b over 2mt, acts as an envelope. And the solution that I'm plotting here is a e to the minus b over 2mt cosine omega t plus phi. Which case is this? This is underdamped. So that is the situation when you have b over 2m less than omega 0, which is square root k over m. Now, if I look at critically damped and overdamped cases where I have no oscillations, we see that x decreases as a function of time, so it's an exponential decay. The strength of the exponential will be different if it's critically or overdamped. So the situation here I have drawn here, the blue one, is critically damped. The solution is x of t is equal to a e to the minus b over 2mt. Omega is 0. Then if I have overdamped case, omega is imaginary. You have b over 2m greater than omega 0, and the solution is x of t is an exponential decay that has a e to the minus b over 2mt times e to the, so let's remember what the solution was here, alpha t, and b e to the minus b over 2mt e to the minus alpha t. So you have additional exponential terms here. So in the critically damped case, we reach the x equals to 0 the fastest with no oscillations. If it's overdamped, it takes more time to reach x is equal to 0. And in the underdamped case, it eventually reaches 0 again, but it's basically inside this exponentially decaying envelope.